Hi, this is a new video in the lecture series Digital Economy and Data Analytics. My name is Eik van Vuren and today we're going to talk about decision trees. Decision trees are a special method or algorithm within supervised machine learning, and even though decision trees themselves are actually not that great predictors, they can be among the most powerful predictors at the moment that they're going to be combined with other methods like random forest and boosting. In order to start with decision trees are methods that divide the feature space into rectangular and disjoint subspaces. These are usually called p-dimensional cuboids. What does that mean? What is a cuboid? Well, a cuboid is actually nothing else as an interval at the moment that we're going to be in a situation in which p is equal to 1. So in the case that we only have one feature, at the moment that we have two features, well, then they are going to be squares. At the moment that we are going to have p equal to 3, then we are going to have cubuses. And in a fourth, fifth, etc. dimension, it's not possible to say anything about that anymore, which makes some sense, but they are generally called cuboids. Well, they are called regression trees when the outcomes are continuous, and they're called classification trees when the outcomes are discrete. That is something that we already know, of course, because of the fact that we do already know that if the outcome variable is say continuous, then we usually talk about regression, so therefore we call them regression trees. And at the moment that we have an outcome variable that is discrete, then at that moment in time we are going to talk about classification, and therefore we call them classification trees. But take into account that most of the idea behind regression trees and classification trees, they are in fact similar. Well, we are going to have that decision trees that have that within a particular subspace. We simply give all the observations exactly the same prediction of the outcome. So that is very special within decision trees, that all the outcomes are going to get, or all the observations that we're going to have are going to have exactly the same prediction. More in particular, suppose that we have m different subspaces and define the mth subspace by Rm. Then the prediction function is going to equal gx, and then at that moment in time we can use the following sum that we have over here. We're going to sum of all the different subspaces that we have, so these subspaces that we have defined over here, and we are going to get an indicator function that indicates only at the moment that x is a part of this Rm that we have over here. Take into account that we have disjoint subspaces, so that implies that only in one of the cases, in one of the capital M cases that we have over here, this thing will be actually equal to 1, and in all other cases it will be equal to 0. And then we predict this Cm that we have over here, where Cm is the predictor for the subspace M. This looks a little bit difficult, but take into account that we could also have written this in terms of Gx is equal to, C1. In the case that x belongs to R1, it's equal to C2, of course. At the moment that x belongs to R2, it's equal to C3. At the moment that x belongs to R3, etc. Now the question, of course, arises, what is then Cm? Well, we're going to talk about that much more, but one thing we can think about is that Cm is going to be the so-called plurality vote in a classification problem. What is that? Well, we have already seen in the last video that at the moment that we are going to go for example, for the situation of k nearest neighbors, that we usually take that particular class or predict that particular class that is the most frequent among all the different classes that we have among the k nearest neighbors. Well, that we can do in this case as well. What we could do is that we could simply take that class within this subspace that we have over here for all the Rm subspaces, which is going to be the most frequent, and that we can do, of course, as well with respect to the Cm. So that means that we are going to have one particular class, say that is class number 3, which is most frequent in this subspace that we have over here among the observations that we have, and then we are going to for any say x that is going to be in that subspace that we have, we're going to predict class number 3. At the moment that we're going to look at the continuous case, well, then we're going to generally do something else. Then we simply take the average among the outcomes that we have in this particular subspace. Well, take that into account that decision trees depend in fact on two sets of parameters. That is first of all the R's, so the R1 to Rm that we have here, the subspaces that we have defined over here, but also of course with respect to the C1 and Cm, the predictors that we have for any subspace. So that means that the minimization problem, the problem that we are going to have here in supervised machine learning is to find R1 to Rm and C1 to Cm that is going to, well, we could denote them by R1 star to Rm star and C1 star to Cm star. That's going to minimize the risk function. And remember that risk function is of course always equal to the expected loss with respect to this y and gx that we have over here. So that implies that theoretically, if we of course would have known this loss function that we have over here, what we need to do is to simply minimize over all the potential subspaces as well as the potential C's that we have over here, and calculate these things that we have over here, and that will then define our trees. Take into account that this cannot be done. This is only theoretically an interesting thing to do, and the reason behind that is because of the fact that we should realize that, as usual, this risk function that we have over here, it is not known to us. So therefore what we could do instead is to try to estimate it, and that we can do by using the training risk. So what we can do is that we can, based on a training sample that is this sample that we have over here, in fact estimate R1 to Rm and C1 to Cm. And because of the fact that these are estimators, we're going to use hats over here. So we're going to have R1 hat till Rm hat and C1 hat until Cm hat, and that's going to minimize this sum of the loss function that we've over here. This is of course nothing else as the estimator. This is a consistent estimator, usually called the training risk, which estimates of course this theoretical risk that we have over here. Well, take into account that this is now all fine. Take another thing into account, and that is of course that one thing we could do then of course is that we could then take into account that, well, the gx that we have, well, that we have already introduced before because of the fact that that's this sum that we have over here. So therefore simply substituting in the gx gives us then this function that we have over here. Another thing that we should take into account is that this loss function, we do of course know this loss function that actually depends on whether we have a classification or a regression problem. In the case of classification, we have of course this 0,1 loss function, so that gives us this loss function that we have over here. So then we are going to get this minimization problem that we have over here, and well, of course also in the case that we have a continuous outcome variable, we do already know what to do, because then in that particular situation we need to have the quadratic loss function, and that gives us then this minimization problem that we have over here. But generally we should realize that whatever we have a continuous or a discrete outcome variable, we are going to try to minimize this we're going to try to solve this minimization problem that we now have over here. As an intermezzo, you might already have seen that lots of the definitions that we have so far with respect to decision trees are actually quite in line with the definition that we had with respect to nearest neighbors. We should take into account that also with nearest neighbors we are going to look at areas, and what we do is that we typically are going to predict, well, based on whether we have classification or at the moment that we have say a continuous outcome variable, we have regression. Either we are going to use the average of the outcomes that we have among the k nearest neighbors, or in the say subspace that we have in the case of decision trees, or we're going to use the plurality fold in the case of classification. So therefore, actually you should realize that k-nearest neighbors and decision trees do have a lot in common. However, you should also realize that there are quite important differences between decision trees and nearest neighbors. And before I'm going to go on, I would like to discuss them actually first. And the first difference between decision trees and nearest neighbors is that in the case of decision trees, we minimize instead of simply choosing the area that contains the k-nearest neighbors. Take into account that with k-nearest neighbors, what we essentially do is that we ad hoc, in fact, take the, say, k-nearest neighbors that we have, and we are going to take there either the average or the plurality vote. That's not what we do in decision trees, because of the fact that we should realize that at the moment that we go back here to decision trees, then the R1s and the RMs, they can actually be quite different from each other in terms of the size that they have, as well as, well, even though, of course, all of them, they're going to be rectangular, they can, well, some of them, they can be quite long and, well, very small in terms of at the moment that we're going to be in the two-dimensional case. They could be very small in terms of height, but others could be completely different kind of shape. So we should take into account that in the case that we're going to look at k-nearest neighbors, then all of the, well, neighborhoods in a sense are going to be more or less identical. However, they can be quite different in the case that we are going to use decision trees, and they're completely based on this minimization algorithm. In addition to that, one thing that I have already said, the subspaces are rectangular in the case of decision trees, whereas they are circular in the case that we are going to look at k-nearest neighbors. And the final difference is that the areas, they are disjoint in the case of decision trees, whereas they are overlapping in the case of nearest neighbors, at least at the moment that k is larger than 1. And that is quite clear because of the fact that at the moment that I'm going to predict 2 points that are actually quite close to each other and k is not equal to 1, well, then you should realize that suppose that this is the first point that I would like to predict, then at that moment in time I'm going to take essentially the neighbors over here, but at the moment that I'm going to predict this point that is actually close by, well, then at that moment in time I'm going to use the neighbors that are over here. And you should take into account that with 2 points that are actually quite close by, they can be more or less the same points. So therefore there are differences between nearest neighbors and decision trees, even though you should take into account also that the two methods actually do have things in common. But now let's go back to the decision trees. We should realize that this problem that we have over here, that we have defined over here, is actually a prohibitively difficult problem to solve. And the reason behind that is because of the fact that, well, it is still relatively simple, of course, if m is not too large, because of the fact that if m is only equal to 2 or 3 or 4, then we could, of course, try to minimize this problem that we have over here. But generally, at the moment that things become too large, at the moment m becomes quite large, then it's going to be prohibitively difficult to minimize this problem over here and to simultaneously determine R1 till Rm as well as C1 to Cm. So therefore what we typically do at the moment that we have the problem that we can actually not solve it, then usually we're going to use heuristics, and that's here the case as well. And first restriction that we're going to make is that the division should be sequentially, and we are going to break up the spaces into only or at most 2 disjoint spaces. So that implies that what we are going to do is that we first of all are going to have the full feature space, and then what we're going to do is that we're going to break it then up into 2 disjoint subspaces. Then we have 2, say, disjoint subspaces, and then what we can do is that we can break these 2 disjoint subspaces up into, well, 4 different subspaces, and then of course 16, etc. So that is the whole idea of these, of this heuristic that we're going to follow. In order to explain this, maybe the best thing to do is now to look at a very simple example. And the example that I'm going to use here is the example that we have already seen before, and that is the example of classification. Remember that in the previous video we have been looking at, say, in a situation in which we have two different classes that are denoted by red and blue. And remember as well that, then we have two different features, x1 and x2. I have here x1 on the x-axis and x2 on the y-axis. And we have, 100 different points which are red, and we have 100 different points which are blue. And then we do already know that our optimal predictor is determined by this decision space, or this decision boundary that we have over here. This dashed line or dashed curve that we have over here. It starts over here and it ends up over there. And also here we have another part of that particular curve. And the idea was that, all the points that are within this area that we have over here, they should be predicted to be blue. And all the other points, so these are the points that we have over here in this left area that we have over here, and also in this right area that we have over here, they should actually be predicted to be red. That is the optimal predictor that we have seen from the previous video. However, now what we could do is that we could try to use trees in this particular case. And then what we could do is that we then essentially need to do in the very first step, taking into account that this is our full feature space, in the very first step what we essentially have to do is that we have to break it up in two different subspaces. That means, of course, that we can do a breakup. We can do it horizontally along the x1 axis, but we could also do it vertically. One thing we could do is that we could simply ask Python to do it for us, and that's what I actually have done. And Python told me that in this particular case, based on the, not of course based on this decision boundary that we have over here, but simply based on the, say, training data set that we have over here, so the blue dots that we have over here, as well this red dots that we have over here, that is our data. Python told us that the best split up that we can do in this case is a vertical one, and it essentially says that we have to do it here at this level that we have over here, which is more or less equal to 1, if I see it correctly. A little higher than 1, of course, and that implies that Python actually says that at the moment that we are going to have a situation in which x2 is smaller than this 1 point something that we have over here, then at that moment in time we should predict blue, otherwise we should make a red prediction. We can actually write that or illustrate that based on a decision tree. That's also the reason why these why decision trees actually get that name, because of the fact that they are they are of course related to the decision trees that you might already know of in operations research. And essentially the only decision that we have to make in this case is whether x2 is smaller or equal to, in this case 1.217. So that is this level that we have over here. If it's below 1.217, then we are going to make a prediction which is going to be blue. And if it's above 1.217, then at that moment in time we're going to make a prediction which is red. So that is as simple as that. And we already have our first decision tree. Question, however, arises, is this also a very good predictor? Well, the answer to that, this is of course not a great predictor at all. This is maybe one of the worst predictors that we have seen so far during this lecture series. And the reason behind that, again, is not because of the fact that we make so many wrong predictions in terms of the training sample that we have over here. But again, what we need to do is that we have to compare that to the optimal predictor, the optimal decision boundary that we have over here. And we do see that that is actually quite different, because of the fact that we do see that, for example, this whole area that is blue, we actually predict here, say, always blue. However, in reality, it should in fact be red, this whole area that we have over here. In addition to that, that's also true for this area that we have over here, that should actually be red, but we actually use blue predictions. And then here we have the other way around. Actually, this area should have been blue, but we actually predicted to be red. So that implies that in this particular situation, we're not doing such a great job with respect to our predictions. However, what we could do is that we could, of course, extend this tree. Trees do not always have just one layer. What we can do is that we can also go for, say, a couple of different layers. And the first thing we could do is that we could now go for 2 layers instead of 1 layer. What does that mean? Well, that means that we have to further break up these 2, say, subspaces that we already have. We have here a subspace over here, and we have a subspace over there, and we are going to break them up into further subspaces. And take into account again that what we can do is that we can make both a horizontal breakup and we can make a vertical breakup. Well, if we are going to do that and we are going to ask Python to do that for us instead, then what we're going to get is then this, say, picture that we have over here. Let's first of all look at the first, say, subspace that we already had. This was the original subspace, and now Python has, broken it up into 2 different subspaces, and in this case based on a horizontal split up. So we now see that if x1 is, say, in this area smaller than, minus a half, minus 0.4, I would say, then at that moment in time we are going to, make a prediction equal to red, and otherwise if it's larger than minus 0.4, then we are still going to have a blue prediction. We see something similar going on actually with respect to this area that we have over here, this subspace that we have over here. Also there we do have a horizontal split up, more or less at the value of 1. So that means that if x1 is in this area that we have over here smaller than 1, then we are going to make a red prediction. Otherwise we are going to make a blue prediction. And in terms of our decision tree is now going to look a little bit more difficult because of the fact that first of all we have to decide whether x2 is smaller or equal to 1.217. If that is true, then we are in, say, the lower, say, subspace, and then we have seen that if x1 is then minus or smaller or equal to minus 0.401, then at that moment in time we are now going to make a red prediction. That means, of course, that we are in this area that we have over here, so therefore we make a red prediction. And otherwise, if we are going to be larger, then we are going to be making a blue prediction. That means, of course, that we're going to be in this area that we have over here, and hence we are going to make a blue prediction. Well, in addition to that, what we can do is that we can also look at the situation in which x2 is, of course, larger than 1.217. Then we're already in this, say, branch over here, and it implies that then at that moment in time we are going to decide whether x1 is smaller or equal to 1.082. If that's true, then we are going to make a red prediction. That means, of course, that we are in this area over here. Otherwise, we are going to make a blue prediction, which means, of course, that we are in this area that we have over here. Well, based on this, we do already see that we may make a much better prediction than we already did before, but still, of course, for example, this area that we have over here, that actually should be making red predictions, but still it's blue. We should realize that that's actually also true for this area that we have over here. That should also be a red prediction, but it is actually blue. And we do see that here it should be the other way around. So this is also a relatively difficult area, but also take into account this generally is quite a difficult area. But we already have it much better as what we have seen before. Question, of course, arises, can we make even better predictions by making further splits? Of course we can do that. And if we are going to go for a third layer, then at that moment in time, what we're going to see is that we then are going to have this area, or then we are going to have this picture that we have over here. So what we're going to see, first of all, at the moment that we're going to look here at the, say, lower right corner, then we do see that that particular subspace, originally we had, this was one subspace, that one is further subdivided into further subspaces, and we do see that now what we are going to have is, we have here another time horizontal split, now at 2.1 or something. And we do see that that implies that if we are here at the left, then at that moment in time we are in this area and we make a blue prediction. Otherwise we're going to make a red prediction. And if we compare that, of course, then also this area that we have over here has a further subsplit because of the fact that at the moment that we're going to look at this one that we have over here, then we do see that actually in this particular situation we're going to make a vertical split here at this level over here, a little over 2 I would say, and that implies that if you're below 2, then at that moment in time you're going to have a prediction blue, otherwise we're going to have a prediction red. So it works again as simple as that, but take into account that there are 2 other, say, subspaces that are no further divided into further subspaces, because here we had original subspace, and we do see that Python actually doesn't want to predict to divide it any further, and that's actually true for this one that we have over here as well. Well, this one is a little simple, and the reason why Python actually doesn't make a further split over here is because of the fact that this is already, well, what we usually call a pure node. What we see here in this area that we have over here, based on the observations, is that all the observations that we have in this subspace over here is red, or they are red. And that means, of course, that at the moment that I would like to make a further split, of course I could do a split over here, say horizontally, I could make a split over here vertically, then still what I'm going to have is that I will make only predictions with respect to red. It doesn't make any sense in this area to make predictions that are going to be blue. So therefore, if I'm not going to make a difference with respect to my predictions, why would I actually then make a further split with respect to this subspace that we have over here? So this subspace will generally never be split anymore. It's a little bit more difficult at the moment that we're going to look at this area that we have over here, because of the fact that this area is not a pure node. We do actually see that, well, there are here blue dots in this red area that we have so far. Also this one that we have over here. So the question, of course, arises, couldn't we do any better by making a split? Well, the answer to that question is that that might be very difficult in this particular case, because of the fact that what I could, of course, do is make a vertical split over here, but then still I get actually quite a lot of red dots in this area that we have over here. I could, of course, also make a horizontal split over here, but then actually also I will actually have a lot of red dots over there. So therefore, in this case, it doesn't make that much sense to actually make a split here as well, even though we do see that we do not have a, say, pure node in this particular case. So therefore, we do see, concluding from this, is that at the moment that we're going to go more and more down, or you're going to make more and more layers, that at a particular moment in time, it might be better to at least have some of the, say, subspaces to not be split anymore. Well, that implies that our final tree is going to look like the following one that we have over here. Well, at the moment that x2 is smaller than 1.217, then we go in the left direction. Then we're going to see that if x1 is smaller than minus 0.4, then we're going to make a red prediction, of course. If that's not true, then we are going to be in this area over here, and then we still have to find out whether x1 is smaller or equal to 2.1. If that is true, then we are going to make a blue prediction. That means that then at that moment in time we are going to be in this area that we have over here. Otherwise we are going to make a red prediction, and that means that we are in that area that we have over there. And well, then in addition to that, if at the moment that x2 is larger than 1.2, well then at that moment in time we have to ask ourselves the question whether x1 is smaller than 1.082. If that's true, then we essentially are going to make a prediction which is red, because of the fact that then we are in this pure node that we have over here. Otherwise, we still have to decide whether x2 is smaller than 2.247. If that's going to be true, well then at that moment in time we make a blue prediction. That means, of course, that we are going to be in this area that we have over here. Otherwise, we are going to make a red prediction, and that means, of course, that we are going to be in this area that we have over here. if we're now going to look at this particular picture, then we do already see that we don't do such a bad job because of the fact that now, in fact, well, this blue area that we're over here already more or less, is related to this decision boundary that we over here. Of course, true, this area over here is not well predicted yet, and also here we are not exactly identical to, of course, the correct decision boundary that we actually wanted. Also here we do make errors, but take into account that actually looks already quite good, especially in comparison to the situation in which we only had one layer. Then finally, the performance of this method is also actually quite good because of the fact that at the moment that we are going to look at the test risk, that is actually equal to 21.3%. That's actually not that much worse than at the moment that we used nearest neighbors in the previous video, because in the previous video we had for k equal to 15, the best situation for k nearest neighbors, we had the situation of 0.2 2021, and also take into account that this is actually not that different anymore from the roughly 18.6% that we would have had at the moment that we would have used the optimal decision boundary, this optimal decision boundary that we have over here. I would like to go on, and I would like now to go on with the next topic, and that is how to build a tree. Remember that what we have done so far is that we do already know what a decision tree is, and we have also been looking at an example, but we haven't really asked ourselves yet how to actually calculate the decision trees. Well, calculating a decision tree is actually a very difficult process, and therefore I'm not going to go into all the different details. However, what I would like to do over here is to give an overview of the decisions that need to be made at the moment that you're going to build a decision tree. In the end, what you're going to do, of course, also during the tutorials, is that you are going to use, in fact, not your own programs, but you're going to use the libraries that we have in Python. But in order to build a tree, what we have to do is that we have to make a decision about the following things. First of all, what should be the simple predictor per subspace, Rm? Remember that what we had, of course, were the, say, Rs, and we had the Cs, of course, the Rm and Cm, where Cm is actually the predictor that we have to make at the moment that we are in a particular subspace. Well, we have already touched upon that a little bit, but it could be better to do that a little bit more formally, and that is what I'm going to do on the next slide. Another decision, and that's maybe the most important or at least the most difficult decision to make, is how do we split nodes into further subnodes. So far I have seen that we could actually do this splits. In the two-dimensional case, that meant actually a horizontal split or a vertical split. We have asked Python to do that for us, but the question arises, how does actually Python do that? That's this second question that we have over here. And then the large question, or the last question, is how large are we going to make the tree? Well, the answer to that last question is actually quite simple because of the fact that that is related to a thing that we have already seen so many times before, and that is cross-validation, or either using cross-validation or using, of course, a validation sample. What we could simply do is that we could start with a tree of a layer equal to 1, then go on to a layer equal to 2, 3, 4, 5, etc. And based on that, what we can do is that we can do either cross-validation or use a validation sample to calculate either the cross-validation risk or, of course, the validation risk itself. And then what we're going to do is that we're going to take that tree, the number of layers of the tree that we're going to use in our final prediction, of course, is going to be the one that is going to have the lowest, say, cross-validation risk or validation risk itself. So that's the idea behind this. Now let's start with answering question number 1. So what should be the simple predictor per subspace Rm? Well, remember that we have already touched upon that. It depends actually on whether you have a regression problem or whether you're doing classification analysis. Let's start with regression problems. Well, then what we usually do is that we are going to take the average over a particular subspace. That is actually quite the same as what we had with respect to k nearest neighbors, So that implies that C hat M is going to be equal to, well, remember this definition, the notation that we also used for k nearest neighbors. What we're going to do is that we're simply going to sum over all the observations that are in this particular subspace Rm that we have over here, and we divide by the number of observations that we have. So that is what we have in the case of the regression problems. In the case of classification analysis, it's a little bit more difficult, but the idea is exactly the same as with respect to k nearest neighbors, and that is that we're going to go for a plurality vote. That means that what we're going to do is that we're going to choose that class that is essentially most frequent in our subspace Rm in terms of the observations that we have in our training sample. How are we going to be able to do that? Well, then the first thing we need to do is to calculate the frequencies. Well, that we're going to do with respect to this P hat MC. M is here for the subspace and C is for the class. And then what we're going to do is that we're going to sum over, say, all the occurrences for this particular, say, class that we have over here in that particular subspace. So we simply are going to count the number of times that we have class C in this subspace M that we have over here, and we divide again by the number of observations that we have in that particular subspace. That implies, of course, that we're going to have, for any class, we're going to have this frequency in this particular subspace, and then what we're going to do is that we simply choose the class that is going to be most frequent. So we're going to choose the class that is going to maximize, which is essentially going to be highest among all these P hat MCs that we have over here. I would like now to go on with the second question regarding building the tree, and that is, how do we split the nodes into further subnodes? In that sense, we typically are going to go for a so-called greedy approach. That implies here that we split the nodes into two nodes which result in the largest reduction of the training risk. For example, we can start here with a regression context, and that implies that we can consider splitting up a subspace Rm. So suppose that we simply have a particular subspace Rm into two rectangular spaces that we're going to denote here by R1m and R2m. So simply, well, one of the parts of this original Rm, we're going to denote it by R1m, and the rest of it, of course, of this original subspace is then going to be called R2m. Well, now we should take into account that essentially implies that we have to make decisions essentially with respect to two things. That's first of all with respect to the feature that we're going to split up. So in a sense we have P different features. So therefore we're going to denote this J for the feature on which we're going to split. And then a second thing that we have to make a decision about is where we essentially are going to split. And that we are going to do with respect to this S. And that implies that we can define the original R1m and R2m, in fact, by an R1mjs. It's a function of both this J and S. And we are also going to look at an RM2JS. And then first of all, the R1MJS, what is it? Well, essentially, it's nothing else as the collection of all the x's in the original subspace Rm that we've over here, but then with the restriction that we're only going to look at those x's for which xj is smaller or equal to s. And then R2MJS is actually nothing else as the rest of the original subspace that we have. So that implies that we're going to look at only all those x's in the original subspace, but for which xj is going to be larger than s. In order to explain this a little bit better, the best thing to do is to go back to this slide that we've over here, and we can ask ourselves the question, we have here a particular subspace, and how can we say divide that subspace into, well, two new rectangular subspaces? Well, take into account that we do already know that we can do that either horizontally along the x1, say, feature that we have over here, or we can do it vertically along the, say, x2 feature that we have over here. But take into account that very generally you can do it, of course, on any kind of feature. Here we only have two features, so it's going to be from the features x1 and x2. But of course, generally we can split essentially on x1, x2 up till xp, of course. And then in addition to asking ourselves the question, well, where do we, or on which, say, feature we have to split, we also have to ask ourselves the question, where do we have to split? So first of all, if we already look at the situation in which we are going to split on the first feature, then of course we can still, for example, split here at 0, or we can split here at 1 or 2, and of course essentially we can split on a whole continuum of all the potential x1s that we have over here. It doesn't have to be exactly at 0, we can also do it here a little bit below 0, of course, or here in between 0 and 1. So that implies that already based on x1 we have a whole continuum of different areas where we can actually split, and that is of course also true at the moment that we're going to look at x2. Then also we can split there, well, horizontally, on vertically on many different levels. So that implies that at the moment that we go back to our definitions of R1 MJS and R2 MJS, well, they essentially first of all determine based on the J, well, on which, say, axis we are going to split. In our case just two axes, but generally we of course have p different features, and the S actually determines where we are going to split. And take into account that if we have already R1 MJS, then also know R2 MJS, because of the fact that that's just the remaining part of this original subspace. But then the question arises, how are we going to determine this J and S? Because of the fact that we would like now to essentially determine J and S in order to make the so-called optimal split. Well, we're going to do that by looking at the maximum reduction that we can have, in fact, in the training risk. Take into account that the training risk, at least among this subspace that we have over here, at the moment that we do a split of R1 MJS and R2 MJS, well, take into account, of course, that we here are going to use this squared loss function. And well, among the observations in R1 MJS, it's simply yi, the observation, minus the prediction that we're going to make, and that is in this case C1 hat. What is C1 hat? Well, that's on the next slide. It's actually nothing else as what we have already determined, well, 2 slides back. It's going to be the average with respect to yi, but in this case among those observations that are in R1 MJS. So that implies that this part that we have over here is essentially nothing else as the remaining training risk over this original subspace Rm that we are going to have in, say, R1 MJS. Well, of course, that's not the only thing that we're going to get. Also, we need, of course, to look at what happens with respect to R2 MJS, and then we get this part that we have over here. And then what we then finally are going to do is that we are going to minimize then this remaining training risk with respect to J and S. And of course, as I already said, well, this C2 hat then is of course this definition that we have over here. So far we have been only looking at the situation of regression. At the moment that we would like to look at classification, then of course we cannot use the squared error loss. However, the idea is exactly the same. What we would like to do is that we would like to maximize the reduction in the training risk, and that we can still do because of the fact that we can then simply replace the, say, error, well, the squared errors that we have over here. We can replace them, of course, by simply the 0, 1 loss functions that we have over here. So the idea is now exactly the same as what we had before, and then what we can do is that we can then again minimize with respect to J and S. So in that sense there is not that much of a difference, but take into account, of course, that the C1 hat and the C2 hat, they are going to be defined a little bit differently because of the fact that well, C1 hat is now going to be the argument that is going to maximize the, well, frequencies that we have, the P1 hat MCs that I define over here, and the P1 hat MC is in this case actually nothing else as the number of times that we in fact have a yi equal to c in this, in this original R1 MJS that we have over here. So it's the number of, observations in a particular class in this, subset R1 MJS that we have over here. And we can do that, of course, with respect to P1 hat MC, but we can, of course, do exactly the same thing with respect to C2 hat. We are going to choose that class that is going to be most frequent among the, observations in the second subspace, and there we define these as P hat 2 MC, and the P hat 2 MCs are actually nothing else as the number of times that we find a particular class C over here in this subspace R2 MJS that we have over here. So that's the whole idea behind this. Then the only thing that we still need to do is to minimize with respect to J and S as we have it over here. But take into account that this actually does look almost identical to what we have seen before, but this actually is quite difficult. And in that sense, it is good to go back to what we have seen before, this minimization algorithm that we have over here. I haven't said too much about it, but we should take into account that since we have here a squared term, a squared error loss that we have over here, we should realize that minimizing this thing over here is rather standard. The non-standard thing is, of course, that we have to do it with respect to the different j's. But finding the s's for a given j is a relatively simple problem. What we can do is to take the first order derivatives with respect to these functions that we have over here, and then essentially try to find, at least numerically, an optimal, level of s for any j that we have over here. And because of the fact that j is finite, this is a relatively simple problem, at least for a computer. But take into account that that's actually not the case at the moment that we're going to look at the situation that we have over here. And the reason behind that is because of the fact that this 0, 1 error loss that we have over here, the 0, 1 loss function that we have over here, is not differentiable. What we should realize is that this derivative is actually always equal to 0, because of the fact that generally this thing is either equal to 0 or 1, but it actually can, it is not continuous at the moment that we, of course, shift from yi unequal to c1 hat to yi equal to c1 hat. And that implies that we can actually not take derivatives over here. And that makes this problem extremely hard for a computer. So therefore, the next thing that we actually need to do is to try to do something about that particular problem. So what we would like to do is to solve this problem. And that implies that what we would like to do is to, rewrite this term that we have over here. Take into account that if I know how to rewrite this term that we have over here, then it would also be possible to rewrite this term that we have over here. So let's go to that particular term, and I've written that here at the beginning of this particular slide. And the first thing that I'm going to do is a very trivial thing, and that is that I'm going to multiply this term by the number of observations that we have in this subspace R1 MJS. That is this thing that we have over here. But at the moment that I'm going to multiply, I also have to divide this. So therefore we get here a very trivial rewriting. Then the next thing that I can do is that I can then actually take this term together with that term that we have over there in order now to have this step that we have over here. And take now into account that, as I already said, this actually has a quite nice interpretation because of the fact that this is actually nothing else as the number of observations that we have in our particular subspace R1 MJS. Well, let's give that a name. Let's simply call that N1 MJS for the number of observations that we have in our subspace R1 MJS. So if we're going to do that, then we are going to get our next step. Well, then the next step to that is that we should realize that at the moment that we now are going to look here in the numerator, then what do we have there in the numerator? Well, it's actually nothing else as the number of, I would say, errors that we make in our particular subspace R1-MJS. It's the number of wrong predictions that we make in our subspace R1-MJS, because of the fact that every time that we make, say, the wrong prediction, yi unequal to C1 hat, well, then we are going to count that as another mistake. So therefore, this can be interpreted as the number of mistakes that we make, the number of wrong predictions that we make in this subspace R1-MJS. Well, we should realize that that's of course equal to the number of observations that we do have in our subspace R1-MJS minus the number of good predictions that we're going to make. So therefore we can also write it in this format that we've over here. This is the number of, say, observations that we have in R1-MJS minus the number of good predictions that we make, for which yi is equal to C1 hat. So this is now the new thing that we are going to have. Well, the next thing that we can then do is to realize that this again, well, is exactly equal to N1-MJS. So we can write this as N1-MJS, and this thing can also be written as N1-MJS in order to get now this relationship that we have over here. Well, then the next step is a very trivial one. We should realize that this, of course, this divided by that is simply equal to 1. So we get 1 minus, and then this numerator divided by that denominator that we have over here. Well, this now looks a little bit nicer, but now I'm going to make it look a little bit less nice. But I'm going to explain you later on why I'm going to do that. Here what we do is that we, essentially take the sum over only those, say, x's that are in R1-MJS. So only those, say, observations that are in this particular subspace. Well, what we could do is that we could also sum over all the observations, but then we need an indicator function indicating that, of course, the particular observation must be in this particular subspace. So we can then write it in this format that we've over here. Then we can do exactly the same thing with respect to this N1-MJS that can also be written in terms of a sum over this indicator function that we've over here. That's actually the definition of N1-MJS. That's actually one step backwards, of course, of what we have done earlier. But the nice thing with respect to this is that we should realize that this is a thing that we have already seen before. In order to make clear that we have already seen this before, what we can do is that we can actually go back to, well, this slide that we have over here. We should realize that what we had in our final step was almost identical to this thing that we have over here. This P hat N1MC. With essentially the only difference that here we have a general class C, and there we had the class C1 hat, the one that was most frequent. So that actually implies that we should realize that, well, we could actually rewrite this thing that we had in the end as in fact the most frequent P hat 1MC. So therefore what we can do is that we can now rewrite our last step in terms of, this is where we were. It's exactly the same thing as what we had in the previous slide, but then with C1 hat. And we can actually write that as, well, P hat 1MC1 hat. And that's actually nothing else as, well, the maximum over all the P hat 1MCs that is going to be the maximum over all the classes. So therefore what we can do is that we now have rewritten our, say, first term that we had, if we scroll back all the way over here, that we essentially had over here, we can actually rewrite in the way that we have done it so far. But that of course also implies that we can rewrite this one in almost a similar way. And that implies that finally what we could say is that we no longer have to do the minimization that we have seen before, but we can rewrite the minimization in this format that we have over here. Take into account that well, this is still difficult for the computer to calculate, because of the fact that essentially we haven't done anything different from what we have seen before. We have just rewritten the difficult problem a little bit in another difficult problem for the computer. So in that sense, nothing has changed, but we should take into account that we did gain something, and that is intuition. What you should realize in this particular situation is that this, say, minimization problem is much more intuitive than the minimization problem that we had before. And the reason behind that is immediately clear at the moment that we're going to look at a situation in which all the observations of a particular subspace R1 MJS, so this subspace that we have over here, are of one particular class. That is what we usually call a pure node. Remember that at the particular moment in time, we have already introduced pure nodes because of the fact that at the particular time we did have a, say, particular subspace that only had red dots, and that we called a pure node already. Generally, at the moment that we have a subspace that has only one particular class, that we call a pure node. The question then, of course, arises, what is then this thing that we have over here? Well, take into account that if there is only one class in a particular subspace, then say all the P1 hat MCs, they're going to be equal to 0, apart of course from one P1 hat MC, because of the fact that that one is going to be equal to 1. Well, with this one particular, say, class that has 100% of the observations, so that means that this frequency becomes equal to 1. And that means, of course, that the maximum over, say, all the different P1 hat MCs is simply equal to 1. That means that we're going to get here 1 minus 1. That's, of course, equal to 0, which means that this whole term is going to cancel out. Well, that helps, of course, at the moment that we do minimizations. Take into account that if we would like to minimize, then it is always a good thing that, say, a particular term, which is always positive or 0, is completely going to cancel out. Then we have the lowest potential outcome. Of course, we do not know anything about this term that we have over here, so we have to be a little bit cautious with respect to that. But generally we can say that it's a very good thing that we are going to have something like a pure node, that we are going to choose R1 MJS in such a way that we are going to have a pure node, or at least a node that has, say, a very high percentage with respect to one of the particular classes, which automatically means, of course, a very low percentage with respect to the other classes. More generally, what we can say is that if we are going to be in the other side of this, if even the most common class in subspace R1 MJS has not a lot of observations, then we are unable to predict the subspace very well. That we can see at the moment that we're going to look at a very simple example. Suppose that we are in a situation in which we have 5 different classes. So C capital is equal to 5, and we are going to have that the highest frequency that we have over all these different classes is only equal to 30%. So there is one class that occurs in 30% of the cases. We should realize that then at that moment in time, if we are going to predict that particular class, then what we're going to do is, of course, or if we are going to predict that particular subspace, then we are going to predict that by that particular class, which means that we are, doing the right prediction in 30% of the cases. But take into account that that's actually not that much different from the situation in which we are going to simply randomly guess, because of the fact that at least if generally there would have been a, say, an equal number of red and blue dots, then already we are going to have, say, 20%, or at least at the moment that the classes are going to be, say, randomly divided. So therefore we should take into account that in this particular situation we are not doing so well, which essentially means, of course, that what we need is a particular subspace which is going to be, unequal in terms of the classes. That's also what we already have seen at the moment that we have been looking at the, say, well, at the moment that we have been looking, for example, at these pictures that we have over here. If you, for example, would like to divide this subspace into further subspaces, then one thing that you shouldn't do is to try to find the subspace which has relatively a lot of reds as well as a lot of blues. So, for example, if I'm going to, well, do something like a split over here, that doesn't make that many sense, because of the fact that then what I'm going to have in this area over here is relatively a lot of reds as well as a lot of blues. It's in that sense much better to do a split over here, which means, of course, that I will have relatively many blues over here and relatively many reds over there. So this is just to conclude that what we in the end would like to have is situations in which the subspaces are going to be very, very unequal in terms of their classes. And, well, take into account that that implies that, well, we could have done that, of course, by doing the minimization that we have over here, but we can also do that with respect to other kinds of measures that say something about inequality. Take into account that the more unequal the subspace is here, the lower this thing is going to be, but we can also do that in terms of other kinds of measures. For example, we can look at the Gini index. That is a general index for inequality. That's this thing that we have over here. Or we could look at the cross entropy or deviance. That's this thing that we have over here. And for example, at the moment that we're going to use the Gini index, then instead of doing the minimization that we have over here, we could as well do the minimization that we have over here. And the nice thing with respect to this minimization that we have over here is that we should take into account that this minimization is actually differentiable, because of the fact that this function that we have over here at least is differentiable in this p hat 1mc. So that is going to be very, very is going to be a very high benefit compared to the situation that we had before. Take into account, of course, that the subspaces that we in the end are going to get by using this Gini coefficient will be a little bit different from the ones that we are going to get at the moment that we do this minimization problem that we have over here, but generally the difference will be relatively small, and it will be a large gain with respect to, well, computing. We don't have to compute that much. So for this reason, what we usually do is to minimize this thing that we have over here rather than that thing that we have over there. And that's exactly also what Python does.